So, hello everyone again. So, so this talk will be dedicated to hyperparameter optimization. During the whole week, we have learned about lots of different algorithms for regression, for classification, and for clustering. All these machine learning algorithms have several hyperparameters. Um, what are these hyperparameters and why they are useful or helpful to be optimized for a data set? We will learn shortly. Let's see implementation of the linear regression algorithm in scikit-learn. Here on the right, we can see different parameters for linear regression. There are two sections, parameter sections and attribute sections. In the attribute sections, we have several, we can say, parameters like coefficient and rank and singular. These are the parameters which are actually learned by a machine learning algorithm. This is what we mean by learning, that an algorithm, what does it learn? These are the parameters which are actually learned by an algorithm, for example, linear regression or ensemble methods or SVMs. And based on these learned parameters, it actually predicts a new sample. Since these parameters are learned based on a data, these parameters are actually to be used for, or these parameters are actually used internally by an algorithm. We should not modify it or we should not change it. However, the algorithm actually exposes several other parameters which can be tuned by a user. These parameters are actually hyperparameters, which can be tuned by a user, and for different values of these hyperparameters, the performance of the respective machine learning algorithm changes. Every algorithm comes with a default value for these hyperparameters. For example, here we can see a fit intercept hyperparameter has a default value called true. And it's Boolean in nature, so it can take true and false both. But we do not know whether default equal to true will be actually best on the data set that we are trying to run it on. Maybe fit intercept equal to false will give better results. We don't know. That's why it's very important to find the right parameter for each value and the overall combination of hyperparameters for every algorithm we are trying to run on our data set, because it varies. Therefore, it's a good practice to start with default values. However, the ideal value remains unknown. We need to find some techniques how to find the best hyperparameter values for each algorithm. Therefore, it's very important to optimize. Why do we need to optimize? For example, we are running one machine learning algorithm and it has n hyperparameters. We can see it, each column is dedicated to each hyperparameter. Now, the first row gives the default value of these hyperparameters. And when we run it on one data set, we get an accuracy of 78%. Now, we are not sure whether 78% is the best possible score. We need to verify this. Therefore, we choose slightly different values of different hyperparameters, and we saw that we improved it to 87%. Then we choose another combination of these hyperparameters, and then we saw the accuracy going up to 95%. However, when we changed again to different set of values, then we saw the actual performance went down to 69%, which is even worse than the default setting. Therefore, based on this observation, we can say that the model 2, or the configuration of the model, or configuration of the algorithm works the best. Therefore, it's very important to verify this, as we have many hyperparameters for any algorithm, and there is no best value defined. There, there are two approaches which we can use for hyperparameter optimization. First one is grid search, and the second one is random search. Grid search is also known as an exhaustive search technique. In this technique, for each hyperparameter, we specify different values for each hyperparameter. For example, hyperparameter for hyperparameter 1, we added 4 values. For hyperparameter 2, 3 values, and for hyperparameter 3, also 3 values. Now, we have added these many values, and we want to search on all versus all combination of these values, which would be 4 multiplied by 3 multiplied by 3, that's 36. In this case, we need to evaluate our 36 models on one data set to find the best one, which means that, for example, hyperparameter 1, the value 0.2 is checked with all the values of hyperparameter 2 and hyperparameter 3. And similarly goes for 0.4 and 0.8 and 1.0, and for all other values. That's why we call it an exhaustive grid search. It's actually an expensive computation because we need to test a lot many models, and it may happen that some of these models are not good and not worth trying. So that's why if we have a very large data set, then grid search may not be a good option to try it out, because it takes a huge amount of time. However, as these 36 models, what we saw here, we need to evaluate, these models are independent of one another. Therefore, the computation of each of these models can be parallelized. To see an example of grid search, here is the hyperparameter search tool in Galaxy. Here is the tool definition. We can select grid search CV tool here, which gives us the flexibility to use grid search. And here at the bottom, we can see there is an option to provide a search list, which is essentially what we saw before. Like for hyperparameter 1, we specified 4 values. Here we can write the name of that hyperparameter and what are all values it should take. Also, the help text is also given at the bottom. We have used grid search in the previous demonstration we have seen for regression and classification. This slide gives you a small example from the regression tutorial. We can see all the different values are filled up for the hyperparameter search. And in the middle, we see the search list. In this tutorial, we were using an ensemble method, and it takes how many estimators for that ensemble method. Here, n estimator is one such hyperparameter of that particular algorithm, which takes 100 as default value. To search for the optimal value, we decided that let's search for values which are also less than 100 and also more than 100, and see if we do any better. In this way, we can specify different value points for each hyperparameter to see which one works the best for that data set. The second one is random search. How is it different from grid search? It actually takes a range for each hyperparameter. It does not take many different value points like grid search. It just needs a valid range. For example, for hyperparameter 1, we can specify 0.1 to 1.0. it randomly samples a number between these two ranges and use it for that hyperparameter. It actually specifies only a fixed number of models. We need to specify, for example, we want to search only for 20 models. Then what happens is hyperparameter 1, hyperparameter 2, and many different hyperparameters, different values would be sampled from their respective ranges, and one model would be constructed and its accuracy is computed. And this goes on for, say, 20 number of times. Again, each of these models are completely independent of one another, and they can be parallelized for faster computations. Here we get actually benefits in comparison to grid search, in terms of we don't need to manually set these checkpoints values. We just need to specify a range and it randomly samples. However, in grid search, we need to manually set these different numbers, which may include some human bias there. This is a less exhaustive search. We don't need to compute all versus all combinations to find the best one. Here is a small comparison between the grid and random searches. More details can be found on the link at the bottom. It's been taken from scikit-learn. Here, what was done for grid and random search approaches, two hyperparameters of one particular algorithm were taken. For grid search, as we learned, we need to specify different checkpoints for each hyperparameter. For two hyperparameters, 10 checkpoints of each hyperparameter were taken, which makes 100 models. 10 multiplied by 10, it gives 100 models. 100 models are specified here. And for random search, we gave only 20 different models to search. We can see the running time of the grid search algorithm is 150 seconds in comparison to around 30 seconds for random search. This whole experiment was repeated 3 times, and we can see the accuracy of grid search in first instance is 93%, the second instance is 92.8, and then third one is 92.7. And also the respective standard deviations in the accuracy is also given alongside. However, for the random search approach, we got actually slightly worse accuracy, which is still comparable, but when we compare it with the running time of random search algorithm, then it becomes a trade-off between speed and accuracy. Here we gain a lot of speed, but we are trading off a little bit of accuracy in comparison to grid search. Therefore, in short, grid search may give better results, but there is huge time complexity for running that algorithm. Therefore, if we have a larger data set, then it may not be a good idea to start with grid search. Maybe it's a good idea to start with random search first and see if the accuracy is good enough. If not, then we can go for grid search, but provided that we have large compute resource. However, if the data set is not that big, then we can straight away use the grid search and get the best model for ourselves. In summary, we can say that there are many hyperparameters for every machine learning algorithm, and default values are given for these algorithms, but they may not be optimal for a data set. The performance of these algorithms differ from data set to data set. Therefore, it's very important to optimize these hyperparameters and find the best combinations for a data set. And to do that, there are two approaches, grid and random searches. If we have a large data set, then a random search may give a better option because it runs faster. However, if the data set is smaller, then they may not have so much of time difference, running time difference. So with this, I would like to conclude my talk.